Today I wanted to discuss some more examples of computational language designs which I've recently worked on. And so here's an example of a Laplacian operator which is using the Chebyshev Fourier method to differentiate, to calculate the Laplacian of a tensor field, a Cartan.jl tensor field, and then apply the Dirichlet boundary conditions on it. So this is going to be our f prime, and then we're going to define a leapfrog integrator, and the way this basically works is you have a leap integrator of second order, and this is just a parameter for the integrator, how many steps it does before saving the result. And then we specify the leap condition with f prime as our function here. And at rest, with an initial leap condition at rest, we put u0 dt and t max. This is the time step and the time duration. So then that leaves u0 as the input, where that's the initial condition basically, and then we feed all this information into an ODE solve. So I modified, I created all these definitions and modified them in my original software to introduce all this. And so we'll do an example here. So we just defined this, and then since this was for the Chebyshev method, we're gonna define a set of Chebyshev points. These are 41 of those, and then we're gonna build a product space out of those as well, like that. And gonna split those into x and y components. And here we're going to define the initial profile u0. Oh, wait, that needs to be capitalized there. All right. So now we have our expression here. So let's take a look at it. So this is the this is the initial profile here, and now we want to plug this into the leapfrog integrator as the initial rest state. This produces TensorField 41 by 41 by 119 And then we can see what it looks like as with the time evolution. And I have a method which allows me to visualize this. I can specify how long the time step is for the visualization. There you go. Okay. So that's solution of the two-dimensional wave equation with the Dirichlet boundary conditions. And the same method can be generalized to higher dimensions as well. We're gonna pick a smaller number of points this time. Now we're gonna go into 3 dimensions instead. Gonna split those. And now we have a 3-dimensional initial condition which we can visualize. So now if we repeat this experiment, in 3 dimensions, this is after evolving it in time, this initial condition, and inside of this box with the Dirichlet conditions. And we can test it at different time steps here. So yeah, this is a very nice unified way of doing things. So the leapfrog method automatically generalizes to any number of dimensions due to the syntax, the computational language design that I've implemented. So it's a very powerful language design that allows this kind of generalization to any number of dimensions for partial differential equations. And we can use the visualization methods that Julia language has to offer to work with these results after calculating them. And yeah, so some more Fourier solution methods that I developed for experimentation. Let's consider the on 0 to pi here. We're going to solve the wave equation with Dirichlet boundary conditions. Oh, yeah, that was... I gotta get this here. Oops, misspelling surface there. So this is the a surface of the time evolution of a particular wave equation on the interval from 0 to pi. And we can actually make a contour plot of this. So it makes this kind of slanted oval mode of oscillation when visualized in the time history of the wave. And we can replace the Dirichlet condition with a Neumann boundary condition very easily just by calling the different function. So this is now what it would look like if it was with, instead of the Dirichlet, we use the Neumann boundary conditions. This is the time evolution of the wave. And similarly, we can do the periodic boundary conditions as well. These are all very standard, so I wanted to have a dedicated syntax for analysis. So yeah, we can see some interesting results with that. And this also generalizes to higher dimensions. Let's define a initial condition function. So this is going to be the rest wave initial condition, Dirichlet. All right, so that's the initial condition right there. And then we can evolve this forward in time. So we can, this can directly solve at any, you can like tell it what time point you want to evaluate it at, and it can directly, you know, evaluate it at that time point if that's what you want. So it just evolves it forwards. And similarly, you can select different boundary conditions. So this was the Dirichlet boundary condition, and you can switch to the Neumann boundary condition very easily. And the periodic boundary condition. So it's very convenient syntax because you can just switch between different boundary condition types that you want to evaluate. Yeah, so another thing that you can do with this is we can create that. We can evaluate this over a time period, and then we can do a variation surface. Yeah. So it allows us to make this animation basically here. And that's with my custom Fourier spectral element solver, which works in any number of dimensions. And you can select whatever boundary conditions you want. Another thing you can do is you can look at the three-dimensional contour of this. Here we can see the time history of as a contour plot. So another visualization of the time history of this would be using the contour command. So if we take a look at this, here we can see how the time history of this wave evolution actually looks like. So this is like a three-dimensional contour plot which shows the time evolution of this wave equation as it evolves in time upwards here. So this is what we were seeing with the variation. So we see this time evolution. And we have a contour plot which shows us the time history here in the 3 dimensions. Okay, and this generalizes to any number of dimensions as well. So if we do x, y, z equals TensorField, now we make a 3-dimensional initial condition. And now we do the rest wave Dirichlet. So here's a 3-dimensional wave. We can see how it evolves forward in time. Well, it just expands initially, and then it starts bouncing off at this boundary there. If we change the number of levels, it's the second boundary there. Now it's on all 3 boundaries there. And now it starts reaching this boundary as well. And this one here. So it's possible to, you know, investigate this step by step, get a sense of how this is interacting with the boundaries in three-dimensional wave equations. And then if you want to switch the boundary conditions to Neumann, that's not very difficult. So yeah, there's some interesting new methods for partial differential equations I've been developing. Yeah, so it's just something been working on, just some demonstration of these things. You can read more about this in my new book. So I published a new textbook where called Principal Differential Geometric Algebra, and you can take a look at that. And if you buy that, there's a lot of information about this and a lot of more other things in there. So about my computational language design, which enable all of this. So if that interests you, these kind of partial differential equations and so on, you can take a look at that. Principal Differential Geometric Algebra. Compute using Grassmann.jl and Cartan.jl is my new book. It's the first book I've written and published, and it's about the programming language things I've been working on. And there's a hardcover and a paperback version. It's 500 pages, with over 500 pages with many different scientifically reproducible diagrams and calculations, introducing people to the programming language paradigm that I've been working with, which is differential geometric algebra, and also some category theory at the beginning here. So yeah, this is a great textbook, new one that I've published. It's the hardcover version here. Got the back side here. So you can read the back side here. Principal Differential Geometric Algebra is the first reference of its kind, built on rigorous category theory foundations and a full unified TensorField computational language design for differential geometry. This category theory foundation presented is a custom designed formalism for categories to specifically emphasize the existence of choice morphisms, relevant to mathematicians interested in how the axiom of choice appears in class and set theory. Next, the book introduces essentials of geometric algebra as the primary basis for differential geometric algebra computational language design using Grassmann.jl library for the Julia language. Developed completely from scratch, Grassmann.jl introduced many pioneering computational language designs to enable reproducible scientific research with numerical differential geometric algebra. Building on Grassmann.jl, the Cartan package is the first computational language design to pioneer a FrameBundle for the PrincipalFiber G-bundle formalism used in advanced differential geometry. Not only does Cartan.jl present completely new programming paradigms for working with an abstract FiberBundle topology using numerical analysis, it also unifies the topological implementations of structured and unstructured finite element methods and also spectral element methods. This book emphasizes the analysis of eigen-characteristics with multilinear algebra, differential geometry, and partial differential equations. Many figures and diagrams are included, all scientifically reproducible with concise programming language. Partial differential equation examples are evaluated with boundary conditions found in the literature to help scientists and engineers validate the usefulness of the computational language design. Also included are many special and elliptic functions and appendices for basics of the Julia language, the Reduce.jl package, the Fatou.jl package, and also the new Unified System of Quantities for physics units from the UnitSystems.jl package. So this is the first edition from 2025 of my textbook, Principal Differential Geometric Algebra, compute using Grassmann.jl, Cartan.jl. So I'm excited about this new textbook. It's now available. Yes, so includes very much interesting information about differential geometry, partial differential equations, geometric algebra. Some category theory as well. So, yeah, I'd be interested to, get people's feedback about this. This is my first book. So, yeah, and if you buy this book, that helps fund my research project in the math and programming language design. So thank you very much for checking it out. It's my new textbook. Yeah, covers many different topics. Yeah, thank you for checking it out.
Product of two things that are parallel is zero. So there's no force on a field-aligned current. So the superimposition of the circular component with the linear component, or an arbitrary angle of input of the current, is, of course, circle plus straight lines field. Now, why they form in pairs is not an easy question. They do. That's a laboratory finding. The little curve on the right just shows the If these things get too far apart, there seems to be a force to pull them back together. If they get too close together, there's a force that pushes them apart. Plasma forms cells and insulates regions